Well, it's nice to see everybody, and it's such a pleasure to be speaking with you all today. It sounds like you've had a really excellent program in geometry, machine learning, and everything in between. And so probably everything I'll tell you about today is kind of old news, but hopefully you guys can tell me what's the interesting next step for our research, and we can work together to come up with some interesting problems to study. Right, it's a pleasure to talk to you all today. I'm calling in from Boston. It's actually a really beautiful day outside, and from my office here at MIT, where, like we mentioned in the intro, I have the pleasure of running a fairly large group that studies problems at the intersections of geometry, data, and application. So, of course, your entire program here is of great interest to me, and I'm excited to learn what you all have been working on. In fact, actually, in parallel with talking to you guys in my other window, in fact, I can't seem to get Slack to stop notifying me as I speak with you. We have a huge group of undergrads and master's students that are also learning about very similar set of topics in a program that we call the Summer Geometry Initiative. If anybody's interested in volunteering or working with this program, do let me know. Essentially, we're looking for people to mentor the next generation, even beyond all of you, I think, in geometry and machine learning research. And we need people to host research projects, just like what it looks like is going on in this LOGML program as well. So anyway, if that's of interest, feel free to reach out to me, and our students are really excited to interact with everybody. In any event, so I'm talking to you from MIT, where I have the pleasure of running a group that we call the Geometric Data Processing Group. I think sort of representative of many of the applications you've heard about this week in your own program. Geometry, of course, cuts across many different academic disciplines and applications. And one of the big pleasures of working in this area is the fact that we get to be sort of consultants and collaborators for a lot of people in a lot of different spaces. In fact, MIT, of course, requires each of us to come up with some corny name for our research group. And in my case, I settled on geometric data processing because I thought that it kind of encapsulates two themes of our research pretty well. So in particular, half of my research group works on algorithms for processing geometric data. So that'll be the main topic of today's talk, techniques for sort of computer vision and computer graphics related tasks involving 3D shapes and the environment around a camera and so on. And then the other half of our group works on geometric approaches to processing data. I saw many of those in your program as well. So for example, we have a long-standing history of working in the area of optimal transport, which is sort of geometry applied to statistics and probability measures. And one of the really fun things about working in this space that I've seen happen over and over and over again is the fact that people working on problems on one side of our group tend to inform problems on the other, and vice versa. So we've had a lot of years of experience building up intuition, working on these very concrete low-dimensional geometry problems, and often those are informing our approach to high-dimensional, more abstract machine learning tasks, and vice versa. So for those of you who are in sort of more abstract-looking data analysis universe, I would strongly encourage you to pay some pretty close attention to the computer graphics, computer vision world, not necessarily just for interesting sources of data and application, but actually for really different and creative techniques to geometry problems that I think we often kind of don't regard as the same community. One of the interesting things I think has happened in geometry a lot, for whatever reason, is there's a lot of different geometry sub-communities. There's like geometry for graphics and geometry for vision and geometry for machine learning and geometry for medical imaging. The reality is that it's the same geometry for all of us. And so there's a lot of benefit to having a lot of collaborations cutting across these different areas. So anyway, there's my soapbox kind of cheerleader speech for you all today. I think essentially one of the really great things about developing skills in this area is just how transferable it is and the really broad set of different places where you can apply your skills. I'm gonna pause for 1 second and see if I can convince my laptop to stop making pop-ups. These guys are driving me nuts. Okay, so for today, as much as I'd love to tell you about every possible thing going on in our group, I'm gonna struggle enough to squeeze in just a few projects into the hour here. And so our focus for today's lecture is going to be on machine learning for geometric data. Now, specifically, a problem that I really care about that we've worked on for a very long time, and it sounds like many of you have developed some expertise in as well, has to do with developing machine learning architectures that can ingest a shape and then learn something about it. And of course, that kind of problem appears in any number of domain areas. So some of the basic ones that I think we can all think of from the applications we see that are pretty popular in machine learning include autonomous driving. For example, here on the left, I show you a point cloud collected by a LiDAR scanner, which is sort of a typical way to collect the 3D environment around a car, to vector graphics, like how you store font on your computer, to triangulated meshes, which are like the things that you render in virtual reality, computer games, and so on. Now, deep learning for geometric data has really evolved over the last 5-10 years. And we were sort of lucky to be in the right place at the right time to be contributing to a lot of these different algorithms. The basic challenges here, before we dive into the details, is that, of course, as all of you know by now, shapes don't fit into the sort of standard techniques that we process data in machine learning, right? They don't have a notion of convolution. They tend to be irregularly sampled. There's weird types of noise that we're not used to from just the usual statistical setting. And moreover, a lot of typical ways to store a shape on the computer are not particularly GPU friendly in the way that like PyTorch and TensorFlow might want them to be. And so back when we started working on all of these problems, these were really big issues and got in the way of applying machine learning methodologies to 3D modeling and LiDAR, virtual reality, these sorts of applications where it's very difficult to walk into the application domain and tell them like, hey, we have this really popular machine learning tool. Your data isn't really compatible with it, but if you change your data, then you can use our cool machine learning stuff. That's not really how that industry works, right? You need to instead adapt your machine learning methodologies to fit into the type of data that they want you to work with, right? I think is a sort of typical difference. This is also a little bit different than some of the computer vision universe where maybe it's okay to tell people to change the way they collect or work with data. Because at the end of the day, the task that they care about is like an inference task or learning about the universe rather than working with a particular data type or file or what have you. In any event, when we entered into this space 5-10 years ago, you can make a very sweeping overgeneralization of the sort of dominant approaches as follows. Now, this is going to be a mildly controversial description of the state of affairs a long time ago, but that's okay. You guys, I can't even see your faces in these little Zoom squares, so I get to do that. Essentially, what I think we saw a lot of geometry techniques doing in machine learning when people were first beginning to experiment with it looked something like this flowchart here, where we had these different machine learning libraries that were popular and easy to use, right? Whether it's PyTorch, TensorFlow, JAX, Keras. I guess these are actually fairly modern libraries, but you could imagine what they were 5-10 years ago. But these libraries were really developed for other modalities, like computer vision from images, or maybe just processing collections of data points. And so now we're presented with some geometry application, understanding a 3D shape or, processing a LiDAR scan. I think a very typical kind of reasoning people would do is say, okay, well, what sorts of things can I do with my geometric data that fit into the computational workflow of these existing machine learning tools? And unfortunately, that's a very restrictive way of engineering, right? Because these computational flows really weren't designed for the type of data that we encounter in geometry. So for example, I think the sort of closest projection of a lot of the geometry problems we've faced in computer graphics onto the typical modalities that are well supported by these libraries will probably be image processing. But of course, the Stanford Bunny in 3D that we have on the right-hand side and like how you might approximate it on an image grid is very different, right? So for instance, we saw early 3D shape processing techniques that maybe would take 3D pieces of geometry, resample them onto a grid somehow, and then apply a CNN. And that's not to say that these techniques weren't successful. They were extremely successful. And it's really important to point that out. That like, it's easy as a geometry person to look at that and say, well, that's like clearly not the right thing to do. That's not how we process shape. And indeed, there are ways to improve that. I'll tell you about many of them today. But one of the really miraculous and exciting things about those initial experiments was that even tools that were engineered for another domain showed promise for like intelligent editing of 3D shapes, understanding environment around us, and so on. But really the question that we're left with is whether we can make a computational pipeline that maybe looks a little bit more like geometry and a little bit less like somebody else's machine learning code, right? In particular, you could ask a question, maybe, oh, yep, which is if I started with the application, right? So rather than sort of, I have a successful learning tool for this other domain, how do I adapt it for geometry? If I say, I have a geometry problem, how do I solve it? And how do I incorporate insight from a data set? Then I think it'll lead you to a very different place. And we're gonna give a lot of examples of that today, where we'll take a look at the typical computational tricks that people do to process shapes, ones that existed long before deep learning was extremely popular. And essentially, by adding a small learnable component to these existing geometry algorithms, rather than throwing your geometry algorithms away in favor of a pipeline that's more compatible with existing techniques, we can have very similar success without having to give up all of the nice sort of classical machinery that we know and love. So I spent a lot of time thinking about the right terminology for describing this approach. And I think all of us in machine learning have a similar discomfort. You know, my background is in differential geometry, PDE, numerical analysis. And of course, in that universe, we spend a lot of time proving theorems and worrying about convergence and sampling and so on. And one of the very first things that everybody's quick to point out about machine learning tools is, well, you know, how little we know about what they're learning and how they're learning it. And that's absolutely right. I mean, I think it's very hard to prove anything about a lot of these architectures, whether they're for geometry or anything else. But the word that I've kind of settled on as a reasonable one to describe a lot of these approaches, and I think this goes not just for like the 3D stuff that I'll tell you about today, but it's sort of a guiding philosophy I see in a lot of these areas. For example, I think this morning you heard from the sort of equivariant, invariant machine learning universe, and I think they have a very similar ethos, which is that we somehow want to build computational tools that pass some basic sniff tests that feel sort of sensible to us. So if you go back to the convolutional neural network, I think this is a fantastic example where, you know, CNNs by themselves, you know, again, we don't know what these image processing machine learning algorithms are learning, right? When you put in this giant data set of photographs and suddenly it's figuring out how to distinguish cats from dogs, the features that are getting learned are wildly complicated. What we do know about a convolutional neural network is that it's built out of sensible units, right? Like an electrical engineer looking at a bunch of convolutions and nonlinearities wouldn't feel that much of a sense of discomfort. You know, like maybe where the weights in the CNN are coming from are a little bit weird, but at least the basic kind of pipeline and processing kind of looks reasonable and is something that you can say something about. I think the early approaches to apply machine learning to geometry did not pass this sniff test, right? They were like resampling shapes in a way that didn't clearly communicate the structure, that often were non-invariant to the kind of things we want to be invariant to, right? Like if I shift or rotate a shape, I don't expect its label to change in many applications. And so I think there was a reasonable effort that was driven by the geometry community to see how kind of sensible looking we could machine learning methodologies we could come up with that can process a shape without foregoing all the computational tools that we like in this domain. So anyway, I think you guys get the point of the sort of high level philosophy that we're after in this little branch of research. And I think it has a lot in commonality with many of the other speakers here and many of the projects that you guys are pursuing. Today, I thought I would squeeze in projects that we have that kind of take that philosophy and apply it to a few different types of data that we encounter in geometry. One being point clouds. This is the sort of the most straightforward modality, vector graphics, meshes. And then I have a fourth project, which is a little bit of an outlier relative to the other three on implicit geometry. That was something we just presented about a week or two ago at CVPR. So in each of these cases, we're presented with a different geometric application, and we're not allowed to go back and tell the application that it should change the kind of data or the kind of computation they're allowed to do. But instead, we want to add a usable and useful machine learning component to this existing kind of toolbox. Of course, I'm just the PhD advisor. My job is mostly just to kibitz and promote all the cool stuff that's coming from my students and postdocs and everybody else hanging out in our group. You know, I'm more than happy to have discussion with all of you today, but of course the reality is if you have hard questions, you should reach out to these fantastic students that I've had the pleasure of working with, who can dive into all the details of these different pieces of research. In fact, I should note that Yue is about to launch his own group at University of Southern California. And of course, if anybody's on the PhD market, I'd strongly encourage you to reach out to him for a possible position. So without further ado, let's dive into some research projects here. And we'll start by talking about machine learning from point clouds. In case you're not familiar, I'm guessing most of you are, a point cloud is exactly what it sounds like, which is just a long list of points. In our case, we'll probably think of our points as embedded in 3D, although sometimes they could be embedded in other spaces, whether it's just an abstract data set, or even in this 3D application, maybe it's XYZ and then RGB for color or something like that. And so you're given a bunch of points that are scattered on some 3D shape. And then there are a number of different tasks that you might consider that happen at inference time, everything from just distinguishing one shape to another, to segmenting all of the different objects in a scene and so on. And I think it's not hard to imagine many different applications in this domain. Now, there are so many challenges that happen in this area. In fact, as much as we'd like to spend all of our time worrying about just like invariance and equivariance and all these cool theoretical ideas, the reality is that the practicalities of working with this data probably put that not at the top of the priority list relative to some really tough challenges, just like loading in these data sets, working with them in a practical fashion and so on. But even from the perspective of the sort of structure in the data itself, there's a lot of interesting headaches that we have to contend with. So for instance, here I'm showing you a LiDAR scene from one of the typical data sets. The task here is you're given the environment around a car and you want to find all the other cars, the pedestrians, the cyclists, and so on. Obviously, this is a really critical task if you want to engineer an autonomous vehicle. Although there's a lot of debate as to whether that should come from a LiDAR scanner or some other 3D sensor. We can defer that discussion for another day. But if you look at this data, you can see all the things that go wrong, right? I mean, the sampling here is far from uniform along the scene. It has to do with the way that the sensor works. The different objects are different distances from the car. They're pointed in funny directions. It's an extremely large scene. And moreover, this object detection task itself doesn't like cleanly fall into the typical buckets that we think about, right? It's not quite the same as just labeling or segmentation and so on. There's a little more to it than that. So from the perspective of the sort of low-level task of engineering a system that inputs a point cloud and outputs something about it, there are already a lot of challenges, right? So point clouds are unordered and unstructured, right? You're given a long list of points, but of course, if you permute that list of points, you don't expect your label to change. There's no notion of patches or local neighborhoods necessarily, at least a priori. And in particular, you can't really develop a convolutional operator because there is no notion of convolution on a curved shape. Now, there are many attempts out there to define convolution-like operators on curved geometry. That's certainly an interesting and relevant direction, but especially in these sparse and undersampled scenes, oftentimes these nice operators that might work on like sampled individual surfaces with kind of uniform and dense sets of points begin to fall apart. And then finally, you do need some means for points to interact with one another. Right? We may not have convolution, but we'd still want some way of communicating information around in a scene. So if you look in the history of machine learning from point clouds, I think arguably the earliest deep learning architecture that was really specialized to this particular type of data was something called PointNet. And PointNet really is one of the more popular pieces of research still. I think at this point, mostly as a straw man of comparison for everybody else's architecture. But it really pioneered deep learning on point clouds. And it did so with a really simple architecture, which is quite straightforward to understand. In fact, it's a little bit miraculous that PointNet works as well as it does for a lot of basic tasks. So the PointNet architecture does the following. It's kind of illustrated on the right-hand side. You're given some point cloud. This is, you can think of it like an n/3 matrix like we've done here. You have this little learnable unit that takes each of those endpoints and embeds it in some other k-dimensional space, and does so without any neighborhood information at all. So every single point in your point cloud just goes through an identical map, like a multi-layer perceptron like you see here, independently of all the other points. Notice that that's permutation invariant, right? Obviously, because I'm processing all the points separately. And now if I want, for example, a label for this entire point cloud, then I take all of these different points in k-dimensional space and I have a pooling operation, which basically summarizes all these endpoints into one. And of course, the design of that pooling operation, again, needs to be permutation invariant. So there's sort of two very simple ones that you might think of. One is summation and the other is taking a max. And up to some bells and whistles, really that was it for this PointNet architecture. And it does satisfy a lot of the desiderata that we set out to satisfy, right? Like it's certainly permutation invariant. It knows something about geometry, right? Like at least, you know, if you kind of co-align the shapes in your data set, maybe it knows that like upper half and bottom half of a shape are different and so on. And in fact, for even fairly complicated shape segmentation tasks, PointNet does remarkably well. I was talking to my friend Max Evyanikov in France, who also works on these kinds of problems, and he and I sort of reached the conclusion that like somehow the success of this architecture is an interesting sort of question about like, well, apparently some geometry problems are really not that hard. That's not a negative thing about ShapeNet or PointNet rather, but rather kind of just, you know, even pretty simple approaches can work for a lot of these types of data. But that said, of course, there's a lot of challenges to working with this simple architecture. For one, of course, there's no notion of local neighborhood. I can't compute something like curvature because every point is processed independently of every other point. And then moreover, if I want a feature for the shape, then there's no local pooling. There's just one big step at the end of the architecture to summarize everything. So of course, after PointNet, there were many attempts out there. One was PointNet++, and another is something from our group that I'll tell you about momentarily, that tried to take this simple architecture and extend it in ways that incorporated more desirable properties for geometry problems. So for example, if we go back to the list of properties we might want for an architecture in this domain, certainly this technique is order invariant. It gets some global information about a shape. But we may also want to add some additional features, like the capability of learning local neighborhoods, like computing things like curvature, which are often important shape cues, or enlarging the receptive field of a point without expanding it to the entire piece of geometry. So back when we were considering this problem, specifically my student Yue Wang came up with a really clever architecture, which has become one of the de facto standards for comparison in this domain. And this was something that we called the dynamic graph CNN, which was built on a simple unit that we called, especially at that time, you needed to add the word convolution in the title of your research paper for people to kind of recognize that as part of deep learning. I think since then, this requirement has gone away. I kind of regret this name a little bit because this is not convolution. In fact, it's actually closer to what we would call attention today, but that didn't exist at the time. But in any event, the basic unit here is quite straightforward. So here's what we're going to do. We have a point cloud. And now to compute a new feature for every point, it's going to gather some set of neighbors, like the k nearest neighbors. And it's going to learn a feature that relates each point to each of its neighbors. So for example, a feature for every single edge in this image here. And now to get a feature per point, we're going to aggregate back from the edges to the central vertex using one of these symmetric operations, just like PointNet. So this is very similar to PointNet. The only difference now is that we're learning a feature for pairs of points and only in a local neighborhood. And then we aggregate back locally in a way that kind of changes depending on your basic location. So this was this module we called EdgeConv. And essentially we can stack them on each other to make this dynamic graph CNN structure here. And this image is illustrating the kind of cool thing that ends up being learned in the structure like this. So here our task is segmenting an airplane, which is pretty simple, right? So we're given a 3D shape and we want to find the wings and the engines and so on. And in this picture, what I'm showing you is distance. So in particular, we've marked a red point here, and then the color goes from yellow to blue based on distance in the learned embedding space, okay? So in the first layer here, this is just distance in 3D, and you can see that like it just drops off from the central red point. And then what happens is that basically the dynamic graph CNN learns progressive embeddings of your data into more and more abstract spaces. And as you do that, the notion of local neighborhood begins to change. So that by the time you get to the end of your architecture, for example, if you look at this point on the wing here, you can see that the points that are nearby, as judged by the geometry of this embedding, are like all the points on both of the wings, right? Because essentially the clever idea that Yue had here was to recompute those k-nearest neighbors in each layer of your CNN. So in other words, your local neighborhood notion kind of changes from one layer to the next. Right, so this was a basic architecture and ended up getting picked up in all kinds of funny places. In addition to graphics and 3D stuff, we even saw it being used in physics and like particle accelerator related tasks, which came as a total surprise to me. UA went on to consider all kinds of other interesting computer vision problems using this basic intuition and architecture. I thought I'd show you a quick sampling of them, although of course I'm already falling behind time-wise, so I'll probably rush through them a little bit. One of the fun problems that we thought about was on shape registration. So we're given two shapes and we're trying to find a way to put them both in the same kind of coordinate system. So like think about walking around a 3D shape and scanning it from different angles. And now I want to register all of those into one kind of simulated scan of a more detailed sample. There's a classical algorithm for solving that problem called iterative closest point, or ICP. ICP roughly, it's one of these algorithms that has a guarantee that looks something like ICP gives you the optimal solution so long as you initialize ICP with the optimal solution. So there's a lot of room for improvement for this algorithm when you don't have a nice estimate of your alignment. What goes on in these deep closest point algorithms, which is a lot of fun, typically the way the ICP algorithm works is it kind of alternates between two steps. First, you compute some rough mapping from one scan into the next. So like this thumb goes to that thumb, something like that. That's one alternation. And then the other alternation computes a rigid motion that matches those points together as well as possible. And then you recompute the map and iterate. Essentially what UA did was replace the mapping step of ICP with something learned. So what it does is it learns features for the two shapes independently, or possibly with some kind of cross-attention style thing to improve the features a little bit. And then essentially computes closest point not in 3D space, but in the feature space, and uses that mapping to bring the two domains together. So here, the learning task is kind of interesting. It's to learn a feature that makes mapping as easy as possible. And if you think about it, those features are not the sort of semantic features we're used to thinking about. These are like useful sharp corners that appear consistently from one scan to the next. And you know, things that are easy to identify and grab onto and so on. But even this simple architecture turns out to do quite well on a lot of registration tasks, with the caveat that, of course, you need training data in some sense. So in one way, it's very easy to do this in a self-supervised fashion, right? Like I can take two scans and simulate them being in the wrong coordinate system by, you know, just randomly displacing them, and then I have a ground truth for how to put them back. But hiding in here is that you learn features that are useful for a single shape category. And then there was a lot of follow-up effort to try and make this generalized and be a more generic kind of registration tool. Beyond this work, there were a number of other projects that we considered. We have a long-term partnership with friends at Toyota Research Institute and autonomous driving. So we have thought a lot about those LiDAR data sets like what I showed you before. Some of the realities of working with LiDAR data, like just the size of the scene, the number of points, and the structure gets in the way of some of these nice machine learning architectures. So the reality is that I think we see these nice geometric approaches being applied in the sort of later inference layers of these things, and maybe the early ones have some of the messy, you know, computational stuff that we still have to do. For instance, last year we shared this object DGCNN architecture for, excuse me, object detection and autonomous driving, which combines some kind of feature map, bird eye view style techniques, which are popular in computer vision community, but maybe don't have the sorts of fancy invariances that we like, with some nice point cloud machine learning on the back end once we can get close to guessing where all the cars are, right? Because of course, there are a lot fewer cars in a scene. There are points that are collected by your LiDAR scanner. One kind of fun paper that I'll point you to, but maybe not describe today, is that UA even demonstrated that this 3D perspective can be useful for basically pure 2D tasks as well. So we applied basically similar architecture to this object DGCNN task to multi-view object registration, where now your input is like just a bunch of two-dimensional cameras on the top of your car. And the only 3D information actually is the camera projection matrix for each of those 6 cameras. And so this technique is actually sort of hallucinating 3D structure for your scene, guessing where the car is, and then projecting it onto those 6 cameras and using 2D convolution to work out a solution to the 3D object detection task, which was a lot of fun. So that was one story in terms of how to engineer a machine learning architecture that can process shape. And if you kind of step back 50 feet, I think what you can see is that we started with the modality we care about, like a big collection of points. And then we went from that to engineering an architecture that has the properties that we want and that ingests the type of data that we care about. I mean, of course, these days people have come up with all kinds of general ways of talking about that sort of reasoning, whether it's, talking about invariances, equivariances, and so on. There's a lot of beautiful theory, but getting your hands dirty and working with a concrete example, I think you find it's a lot less complicated. I mean, we were able to do this in a representation theory-free way here, at least unless you start digging into the details too much. And indeed, in a lot of these other domains, we can take a similar approach. For example, we have a number of projects involving vector graphics and computer graphics. This is a very different type of geometry than a point cloud. In some sense, it's like on some opposite extreme. So in vector graphics, sometimes we call this parametric geometry. You typically have a very sparse set of shapes that are very carefully chosen, right? So it's not like a dense sample of points. But for example, if you have a font, then you have an artist that very carefully placed these spline curves along the side of the font. And these are the kinds of things that you're comparing. So typical applications in this domain are quite different from the point cloud ones. I've shown you a few of the ones on this slide. I think the most popular one that we see a lot of is vectorization. So for instance, in the upper left, I show you an image from a computer graphics paper we had where we're vectorizing a hand-drawn sketch of a hippo here. But very similar style machinery is also used, for example, if you want to extract a roadmap from a satellite image. Sketch-based modeling is another fun example of a very clearly kind of machine learning task. There's a lot to be learned here and a lot of priors that you need to be successful, where you take in maybe a sketchy 2D image and you want to generate a watertight 3D thing that you could print. And then finally, a popular task in computer vision community, I will admit that I don't jive quite as much with this task. I don't quite understand exactly why people want it, but it seems to be popular for some reason in publishing, is this idea of shape abstraction, where maybe you have some complicated 3D or 2D shape and you want to summarize it with like a few primitives or something. If somebody knows exactly where this gets used in practice, I'd actually love to hear it, because our group sometimes gets forced to compare on these data sets and I can never quite tell if we're successful. But in any event, hopefully you see why this data is quite different. For example, this letter K here, notice there's like, what, 10, 20 curves rather than like a dense sampling of points on the outer part of the letter. Now, a typical theme that shows up when you're processing this kind of geometry is an interesting transition between Eulerian and Lagrangian data. So a typical piece of data in computer vision oftentimes is Eulerian when you're working with photographs, meaning that you have some grid of numbers. So for example, here, we all see the letter K, but the reality is that this is an image where like you have a bunch of squares, each of which are pixel colors that are either black or white. And maybe in this funny shape abstraction task, your goal is to input this image here and output a Lagrangian representation, which would be like control points or like endpoints of a bunch of curves covering your shape, right? So Eulerian data is like things that happen on a grid where the grid is sitting behind your piece of geometry and not moving. Whereas Lagrangian data would be stuff that moves, like points, and you're parametrizing from the position in the plane. And in almost every architecture that I've encountered for vector graphics, essentially the main challenge is how do you transition from one to the other? For instance, in sketch-based modeling, maybe you collect your sketch image as Eulerian thing, like literally a photo of a sketch. But then the Lagrangian thing, like the control points of the 3D model, is what needs to come out. So we've thought quite a bit about different approaches to this task. And my student, Dima Smirnov, sort of had a useful high-level approach that seemed to carry through a lot of his different research papers, which looks something like the following. So let's say that this red curve is in a Lagrangian shape. So it's like actually some curve that's parametrized by the endpoints and maybe tangents, the usual stuff that you see in like, I don't know, Adobe Illustrator or PowerPoint. And you have some Eulerian data sitting behind it. You want to measure how well these things align. Then you need some differentiable functions that can link those two things. Then basically Dima's high-level observation is that if you fix any point on that image grid and you compute its distance, like the closest distance to a point on that curve, that is a differentiable function of the control points of the curve, right? So as I move this curve around, its distance to each of these points on the underlying grid is something that I can compute and differentiate and incorporate it into my machine learning pipeline. And it turns out that you can write a number of different loss functions that people care about for like aligning shapes together, trying to make the tangents line up and so on, basically just in terms of these simple distance field style losses. And when I say distance field, I don't necessarily mean like these learned sign distance fields that are popular right now, but really just computing distance in closed form to like a parametric curve, like a line segment or something like that. And this led us to a number of different machine learning pipelines for useful shapes. So originally we considered some problems in 2D where maybe you ingest an image and output some control points. And then your learning loss functions tend to be things like alignment, how close things are, chamfer loss, and so on. And when we did that, essentially by applying this simple reasoning, we're able to solve some very, very kind of straightforward tasks like things involving interpolating between fonts, seeking and searching, and so on. One kind of interesting takeaway was that actually these sorts of loss functions are not just useful for machine learning tasks, but also low-level geometry tasks as well. So we actually went back and worked on a meshing problem in scientific computing that has nothing to do with learning at all, but it's actually reusing a lot of our same PyTorch code behind the scenes, in this case to extract a hexahedral mesh of a 3D model rather than to like come up with an interesting label for a font. Now, working in 3D, some of these kind of loss functions become more challenging to work with. So in 3D, oftentimes we're working with parametric geometry that's built from a bunch of patches. So like here, let's say I want to model a bathtub. A very typical way that I might do that would be to come up with the topology of the bathtub as a bunch of pieces like on the left-hand side, and then to maybe control the corners of these shapes and kind of how they glue together. And then your machine learning task for sketch-based modeling might be something like input a sketch image and then output the sort of control points of all these 3D surfaces. Now, those sorts of alignment loss functions, like I mentioned before, become really difficult to measure here because you need to be able to sample data on a grid. And of course, 3D grids are very tough to work with. So going back to some of these loss functions, what we found is that we could go back and express many of them as integrals over the surface that we're trying to compute and predict using our 3D modeling tool. And of course, surface integrals look very complicated and are things that we don't typically encounter in machine learning, but actually are quite straightforward to measure in the context of stochastic gradient descent, because of course, this is nothing more than the expected value of some function on your surface. So long as you can randomly generate samples, you actually can evaluate a lot of these classical loss functions that people often use in like geometric flows, just in the gradient descent setting that we care about in machine learning. In any event, here I'm rushing a bit through this part of the talk because I'm behind and would prefer to tell you about some newer stuff. But again, the basic point here is that here we're presented with a very different type of geometric data. Like our shapes are comprised of like very sparse and carefully curated sets of large patches rather than very densely chosen points. And what we end up with is a very different computational pipeline for how we might do machine learning and inference with this type of shape. So let's see another example of that in a different type of modality that's also popular in the computer graphics world, and that's triangle meshes. So many of you have probably seen triangle meshes in the computer graphics context. Essentially, the most famous triangle mesh out there in the graphics community is the one I'm showing you here. This is the Stanford bunny. But essentially, a triangle mesh generically is just a big collection of points, like a point cloud, now linked together into a little triangle topology to cover the entire surface. So learning tasks for triangle meshes is a relatively new domain. There's still a lot to be done in this space. I'm always happy to tell you about more. But the basic task here is to like ingest one of these meshes and come up with a label or a means of editing it and so on. It's a really important task in computer graphics. Now, the reality of mesh processing with machine learning for a long time was that probably state of the art quietly was something we didn't like to talk about, which was you throw away the triangles altogether, you just keep around the vertices and you use one of these point cloud neural networks. And I think up until maybe a couple of years ago, that probably would have gotten you pretty high performance on a lot of the triangle mesh benchmarks. Of course, the state of affairs has changed since then. But once again, triangle meshes are really interesting and weird species of data that are tough to work with. Now, I know that on your program in this conference this week, you've learned stuff about graph neural networks. The very first question you might ask is, well, a triangle mesh is just a graph, right? It's a bunch of points connected into a network. You know, are these GNN architectures relevant here? And the answer is, of course, yes. But in some sense, we have to be quite careful how we apply them, because the network structure in a triangle mesh, in some sense, is exactly what we want to quotient out, right? Like a triangle mesh, the interesting part is the geometry. Like the particular ways that we choose to place triangles are less important. And oftentimes, in fact, in geometry, we talk about remeshing and flipping triangle edges and so on as ways of simplifying and improving essentially the same expressions of the same shape. So while we might want our machine learning architecture for a graph to be extremely sensitive to the topology and connectivity of the graph, because that's the sort of relevant signal, here, that's almost something that we want to get rid of. It's a bit of a delicate balance, but I think you see that these techniques look very different than GNNs. Although I do wonder if there's some intuition that's been built on the mesh processing side that would be valuable for graphs as well. Now, if you dig into the geometry processing literature and you say like, well, 10 years ago, before people were doing deep learning on shape, how did they recognize like this bunny here? A lot of the techniques had a very similar flavor. And they made use of an area of math called spectral geometry, which looks something like this. If you're unfamiliar with spectral geometry, the basic idea here is it's built on a very famous math question from, I think, the 1950s, 60s, which was whether you can hear the shape of a drum, right? So the basic mathematical question was, you look away from a 3D shape, somebody taps on it lightly. We're not trying to break it. We don't want to break our bunny here, and we hear a knocking sound. And now we observe a list of frequencies, like vibration frequencies that object made. And the question is, can we use those vibration frequencies to actually reconstruct the shape? And so that's the sort of high level approach of spectral geometry. And from a machine learning perspective, it's actually quite attractive, because the list of vibration frequencies is kind of like a feature vector, right? It's a long list of numbers that describes the shape, which is much easier to work with this giant interconnected network of vertices. So that's what we saw early shape retrieval algorithms doing. They would compute like vibration frequencies, use as a feature, and then maybe index into your data set that way. Now, a spoiler alert from spectral geometry, it turns out there do exist isospectral shapes, like two shapes that are indistinguishable from this perspective, but they're actually quite hard to find in practice, and theoretically for that matter. And there's a lot of mathematical theory telling you exactly what you can learn. Now, if you dig into the theory a little bit more, essentially what you'll see is that this is all built on eigenvalue problems. So you're given a shape, you construct a very particular matrix called its Laplacian, and then essentially these vibration frequencies are exactly the eigenvalues of the Laplacian. This is a very typical way in geometry to kind of featureize a 3D shape, is to take your 3D shape, construct a matrix out of that shape, like this delta here, compute it, that list of eigenvalues of that thing, and then use those as the feature. Now, back when we used to work on these problems, these were very carefully designed matrices and eigenvalues and eigenfunctions, right? We would like take our favorite PDE, like the heat diffusion equation, write down the sort of relevant spectral problem, and then carefully cook up a feature, kind of similar how in image processing people would cook up, maybe the SIFT and SURF features for an image and then construct vision algorithms out of that. But one of the earliest architectures for actually learning using this spectral approach was proposed back in 2014 by Littman and Bronstein. And there they made a really simple observation, which is just, if you go through a lot of the different algorithms people were using for coming up with descriptors or features for shape using this Laplacian approach, they all basically could be encapsulated with a single formula where you take the Laplacian, you compute its eigenvalues and eigenvectors, and then you just apply some carefully prescribed functions to the eigenvalues to construct your descriptor. And so what these folks proposed was just learning that function. This is a one-dimensional learning task. Essentially, you're just taking the vibration frequencies and kind of figuring out the best way to mix them together to solve a given geometry task. So you could ask a higher level question, which is the one that we set out to answer about a year ago, which was essentially, there are many different physical systems and dynamics that can be used to describe a shape. So maybe rather than like very carefully coming up with the bespoke system that describes the shape property we want to be sensitive to one at a time, we could try to actually learn that as well. Namely, that matrix that we're constructing, in spectral geometry, this Laplace matrix, is this carefully prescribed thing in a lot of these early algorithms, but maybe instead of that, we're actually going to learn the matrix that we work with itself. Now, if you've heard about graph neural networks, you've probably heard about Laplace operator or matrix there as well. And this is the same Laplacian. I mean, people in geometry construct them very carefully, but the reality is the formulas look nearly identical, right? So at the end of the day, the way that we can construct these Laplace matrices, basically, there are a lot of different formulas out there. The one that we chose to build on is from a piece of machinery called discrete exterior calculus. This is a trendy tool in geometry, but I'm guessing has not penetrated the machine learning community quite so much. But it's essentially a way to build up a calculus on a curved domain that has a lot of the nice properties from the smooth case. In discrete exterior calculus, you can write the Laplace matrix in a nice factorization, which looks like the product of something combinatorial. That's this D matrix here. And then basically a feature per edge and per vertex, which is the star matrix here. So without diving into the details of exterior calculus and Hodge Laplacians too much, I think the real takeaway from discrete exterior calculus is that it gives you a factorization of the Laplacian, which is actually really simple. This carries over again to graphs quite easily, right? So one of the ways that people write the graph Laplacian is a sort of differencing matrix that subtracts values along edges, which is conjugated around a diagonal matrix, which is one feature per edge. And this is sort of the analogy of that on a triangle mesh. But essentially, what we can do is pose our machine learning task as learning these star operators, which at the end of the day is just one feature per vertex or per edge of this mesh. So at the end of the day, this is a very simple thing to learn because the Ds are combinatorial. We don't have to touch them. All the geometry task that's happening here is just learning a local feature, which is something we do know how to do. So by looking at that simple formula, that led us to propose this architecture for learning from geometry we called HodgeNet, built on these Hodge star operators, where here I've shown you the learnable units of HodgeNet in yellow, and everything else is kind of prescribed. And again, remember our goal is to look sensible from the perspective of a geometry processing researcher who's used to working with meshes and maybe is not so comfortable with this machine learning tools. So one thing that you'll see is that this workflow looks very similar to these classical spectral geometry shape features, where what we do is we input a mesh and we construct what we're calling the HodgeNet operator, but what classical people would just call the Laplacian, where essentially it's built out of combinatorial things, these Ds, and then very simple features per edge and per vertex that are just built out of like the one ring of vertices near a central thing. So these as learnable units are very simple. They're built from very few learnable parameters because all they know about is like maybe the two adjacent triangles to an edge. Then we compute the spectrum of this operator, so the eigenvalues and the eigenvectors. That should raise a red flag to all of you because these are giant matrices. There's like on the order of tens or hundreds of thousands of vertices for a single triangle mesh. So this like arrow here is really suspicious. We'll come back to that in a second. And then from there, the only other learnable thing is basically sort of a copy of that previous Lippmann and Bronstein paper. Like once you have the eigenvalues, now it's just a 1D learning problem. Now, essentially what we showed is that many of the different benchmark tests in 3D learning, you can get state-of-the-art results with this architecture, and it's actually extremely lightweight. That even though this looks complicated mathematically, the number of learnable parameters here is very small. It's just these simple star 0 and star 1 features. The only challenge is how to backpropagate through this thing without using up a huge amount of computation. And once again, we resorted to the same intuition, which is that if we lean on techniques that are successful in geometry rather than techniques that are successful in learning, oftentimes we can get a lot of benefit. So in particular, this architecture, we actually implemented completely on the CPU rather than using the graphics card at all, because the reality is that GPU computation is really tough on triangle meshes. And in particular, inverting or computing the low order eigenvectors of a sparse matrix is just not a well-supported operation in PyTorch or TensorFlow. Maybe I'll defer because we're a little bit low on time, exactly the theoretical result here. But one thing that you can show is an approximate backpropagation formula where if I only know the top k eigenvectors of a matrix, I can still get an approximation of the sort of backpropagation gradient that I should use, which is suitable for this style of computation. So at the end of the day, the forward pass in our computation looks like just standard geometry processing, like computing a few eigenvectors of a giant matrix rather than the full set, which is what the default would be in these deep learning pipelines. And then during backpropagation, we had to write a custom derivative formula that can kind of make do with the fact that we don't have all the information we'd like to have. But the end result here is that we end up with a really nice learning technique for triangle meshes that has the added benefit of actually really nice scalability because we're not using the graphics card, right? One of the big challenges using GPU for these really large meshes or even graphs is that you can't even load it onto the GPU one data point at a time. Whereas these numerical linear algebra tools on the CPU are really built for this extremely large scale environment, which is quite nice. Now, I don't know, in a couple of years, this might change. It seems like there's a lot of effort to come up with really clever GPU operations that can deal with this sparse irregular structure of a mesh. But at least as of now, this sort of technique seemed to be a reasonable trade-off. Now, I only have a couple minutes remaining here, so I don't have time to dive into the details of the last project I wanted to share, but maybe I'll give a quick high-level kind of intuition for a really fun research paper we just released. And of course, I'm happy to answer more questions about it, or I can point it toward you to take a look at offline. And that's in the area of implicit geometry. So just in the last couple of years, a new kind of popular way of doing 3D modeling with machine learning is to use implicit shapes. So to like think of a shape as the zero level set of some function, and maybe we express that function as a neural network. And that's a really fantastic idea, and it's extremely impressive, the things that people are able to do with this new modality. But it has a fundamental limitation, which is that, of course, if I think of a shape as the zero level set of some function, and my shape can never have a boundary, right? It has to be closed because that's sort of just a basic property built into the math of working with differentiable objects. And so one kind of base level problem we set out to think about last year involved how can we develop implicit modeling using machine learning that can deal with shapes with boundary. And that led us down a really fun rabbit's hole involving a very different area of math, which is geometric measure theory. Without going into too much detail, essentially geometric measure theory is the area of math dedicated to solving problems like plateau problem, where I'm given the boundary of a shape, like think about like a piece of wire in 3D. And then the variational problem I want to solve is to like find the surface with minimal surface area whose boundary is that piece of wire. And the basic observation in GMT is that I can write a problem that almost looks convex in a really strange variable called a current, which can solve this plateau problem implicitly. So this is sort of like working with some analogy of Dirac delta function. You like learn a function on 3D that's peaked right along this thin slice of space where your surface is living. That's the basic point in this GMT area, which I am summarizing extremely informally. I should be careful here. Now, at the end of the day, the optimization problem for computing a minimal surface in this domain is really simple, which is super cool. And I think totally non-obvious if you crack open one of these math textbooks. It looks something like this. So essentially, let's say I want to come up with the world's most complicated way of computing a line segment. So I'm given 2 points and I want the line segment between them. Here's the GMT way that I would do it. Given the boundary of my domain, so in this case, 2 points, there's a particular vector field, which we'll call A sub alpha sub gamma here, which is just a formula in terms of the boundary. And then basically in GMT, to find the minimal surface, you look for a second vector field that tries to cancel the first one out, but has to do so in a very particular choice of norm and only in the space of gradients of functions. We'll save the technical details for later, but essentially the optimization problem takes this alpha function, computes a function f, and when we look at the norm of the sum of these things, you can see that it's concentrated just along that straight line. And so just last year in computer graphics domain was this sort of problem was introduced as a way to compute minimal surfaces for 3D modeling. And one of the really cool things that we noticed is that this problem fits really well into the deep learning kind of formality. We can understand the objective function like an expectation, and the constraints are quite easy to implement with the neural network. This is really a surprise. I mean, I don't think differential geometers are used to thinking about using stochastic gradient descent to like predict bubble film shape. But beyond that, we can actually apply it to some fun 3D learning tests. So first of all, we can solve minimal surface problem. Here, these surfaces on the right are actually parametrized with deep networks, which is kind of funny. But beyond that, really, of course, what we want to learn is some 3D surface like this guy. Notice he does have a boundary. But of course, if we compute the minimal surface, we get something like a potato chip. It hardly looks like this face here. So in order to compute a minimal surface type object, but get a more interesting type of geometry like this 3D surface here, the way that we do it is by making a simple observation. Essentially, the point here is that rather than optimizing for a minimal surface in the geometry of R3, we can put a Riemannian metric on that space that makes it cheaper to place surface area close to the surface we're trying to model. And now suddenly the minimal surface, the surface with minimum surface area, changes because it's cheaper to put surface area in some parts of space than others. So essentially, this is a really funny way to do 3D modeling, where rather than modeling the surface directly, we're modeling a Riemannian metric in which our surface is a minimal surface. And this turns out to be actually a pretty practical technique in some sense. So for example, here, if we want a circle instead of a line, we just add a bias to our optimization problem, which makes a Riemannian metric being kind of cheap in the directions of our circle. And now when we solve that problem where f changes and out comes this other function. So we showed that this is extremely flexible surface representation, and in fact is compatible with a lot of different learning tasks, because now we've exposed the boundary of the surface, like where we're cutting it off from the interior geometry. So for example, here we're showing you surfaces where we fixed a latent code that's describing the shape of the surface. We're changing that thing around while we fix this boundary, which is really important for tasks like 3D modeling, where maybe I model this hand, but I have to glue it onto the rest of somebody's body, and I need to control the interface in between those two things. Or vice versa, we could maybe choose a careful latent variable and play with the geometry of the boundary in order to like glue it onto a surface. Now, we're continuing to think about all kinds of fun problems in this implicit modeling space. Actually, just yesterday, we had a paper accepted that's describing a technique for 3D animation built on kind of similar machinery. So I encourage you to take a look. One of the really fun things about working with these neural representations is they're a little bit less topology sensitive, which is kind of nice. But in any event, I know I'm out of time, so we'll stop here. But I think the high level takeaway is that, A, there's really fantastic applications in 3D geometry, vision, computer graphics, but each one of them demands a very different approach to machine learning. These are very specialized modalities, and ingesting each of these different types of shape and manipulating them in an interesting way requires a mature understanding, not just of the learning tools, but also the preferences of that particular application domain. So in some sense, there's a lot of room for expertise, whether you're a mathematician or a data scientist, and really a lot more to go here. So in any event, I know I'm about at the end of the hour. I'm still happy to answer any questions people have or hang out as long as you like, or you're always welcome to reach out to me on email, Slack, whatever. I'll admit that I'm not watching your Slack very closely because there's a lot of messages and I kind of got confused. But in any event, it's my pleasure to speak with you all today. Please keep in touch, and yeah, I'm happy to chat an hour later. So thank you very much for your time.
Wonderful. Thank you so much, Professor Solomon, for that wonderful, wonderful talk. And I think we have time for a few questions, so I'll open it up to the audience now. We have 2 questions from Milton Wong, if they are in the room. But I don't see them. So the question is, so they have questions about a shape matching problem. So if we want to build, so first question, if we want to build an embedding of the 3D object in the local level rather than globally, does it mean the desired embedding refer to the one which preserves the geometric information to the most extent? If yes, what exactly are such geometric information to be preserved? What constraints should it satisfy?
I'm not sure I totally understand the question, but I'll answer the question I want you to ask me instead. Right, so there's a reasonable question hiding here, which is essentially, I think especially, it sounds like you guys have heard a lot of talks about invariances and equivariances and so on, and I'm talking about local geometry. How do these two things plug in together? I mean, the obvious invariances we often talk about involve, like, if I take a 3D shape and I rotate the whole shape, I don't maybe expect my features to change. But things get a little bit more tricky than that in computer graphics style applications. So for example, maybe I have a 3D hand, and of course, as I bend, some features change because obviously a joint has changed, whereas others remain the same. I think it's really difficult to define a feature that you want to preserve with an exact equal sign from local geometry. I think everything here is a lot fuzzier. In fact, I think you see that built into a lot of the early literature. So one very typical motivation you read at the beginning of these machine learning for shape papers that use Laplace operator is that like, well, any good shape feature should be isometry invariant. I take a surface, like this sheet of paper here, and I bend it without stretching, then my features shouldn't change. And that's important because humans are articulated, and if I bend my arm, then like I don't want the feature of the individual points to change that much, which is great until the task for my machine learning problem is find me the angle that my arm is bent at, in which case I threw that information away at step 0. So I'm not sure that I'm answering the question that we got, but essentially I think we have to be so careful when people ask like, well, what must we be invariant to? I think the answer is probably nothing. I mean, there are even cases where like 3D position is a totally useful cue in itself. Like if I'm looking at a scene, distance from the floor is often a very useful thing. So rotation invariance could actually not be what I want. In fact, like the Kinect is a good example of that, right? Like the Kinect computer vision system, if I flipped it upside down, like if you have a Kinect at home, you just put it on its head, it'll stop working, right? And that's because most humans stand on their feet, and that's useful information. But at the same time, it might be that if you know a little bit more about your problem, like you want to be invariant to certain motions, you can build that in. But I think it's really important to do so in an approximate fashion. And I think that's something that's a little less explored. I think we see a lot of really popular algorithms right now that like build in really cool invariances into neural networks. I think there's a really interesting question, which is how do you learn which invariances are important for a given data set? A, and B, how do you learn how much wiggle room there is in these different modes of deformation? These are really important in practice and things that I think are understudied. How's that for a total non-answer to your question?
Thank you for that answer. Milton, I think I see Milton in the call, so if they want to kind of chime in, they're most welcome to. But they also had a second question, which is deep closest point method suitable for non-rigid shape matching problem and integrated into functional map framework?
Oh, okay. So it sounds like maybe Milton knows a little more than I do about some corners of this area of research. Yeah, so the original architecture was intended for rigid shape matching. I think if you incorporated a shape feature like this DGCNN thing, which has a hope of using local neighborhood, then maybe you could adapt that architecture to non-rigid mapping. But as it's written down, it wouldn't be suitable because at the end of the day, it's outputting like a rotation matrix, right? So like if it's one rotation matrix for your whole shape, then obviously non-rigid stuff won't work. I think if you look spiritually at these deep functional maps papers, there are a lot of things in common, right? They're doing some very similar things, but they do so in shape feature space rather than just on the 3D position. I haven't seen a paper that brings those two things together, but maybe Milton will be the person to do it.